our idea of how we can build up a demonstration, the next stage would naturally have been to say, okay, can I take the smart timer, build a platform driver for it, and then talk to it from Linux, right? And what I want to do over here is I want to actually take up something slightly more complex than the smart timer, right? And in this case, in the previous set of videos, we talked about the FFT, the Fourier transform. Here I actually want to talk about something which is of similar complexity to the FFT, but probably a bit easier to understand, right? Which is a finite impulse response filter, which is a common kind of peripheral that you might want to implement in hardware. It is one of those things which is very well suited to implementing on an FPGA, right? It has a large number of multiply accumulate operations that need to be performed, so it's just about perfect for an FPGA. It requires you to implement things using fixed point computation, which cannot be done very well on software. So all of those things need to be taken into account. So what we are going to do is take up a very simple example of that, just a 4-tap FIR filter, and see how we might go and implement something of that sort in our hardware. Okay. So I will also be talking briefly about fixed point arithmetic, although it's assumed that you already know this. This is more of a refresher, right? This is already something that was covered in the digital design course in some amount of detail. We'll also be using the vector mode data transfer pattern that we used in the FFT example. And other than that, the same co-simulation principles apply. We'll be using a Linux driver and a Renode co-simulation. So this will effectively be a full stack, right? We have RTL, we have a Renode platform, and we are actually running an operating system on it. So this part of it is pretty much, of the presentation is pretty much a recap of material that's already known, but I'll just go over it for completeness. What's a finite impulse response filter? It basically assumes that you have some kind of input, right, x of n, samples that are being received from, it could be from an A to D converter, it might be being read from disk, it might be coming from a network, the source doesn't matter, this is a set of numbers. Now of course in digital systems numbers are represented using a finite number of bits. So I assume that there is some bit width that is associated with this x of n, right. There are also a few filter coefficients or taps, right. These C of k, in our case I am going to consider just 4 of them, right. There are exactly 4 taps over here, I am just going to consider that these are present. These 4 taps essentially correspond to a set of values which I need to multiply with my x of n, right, and add them up together, and this produces the filtered output. Now there are a few numerical properties of systems like this which I am not going to get into because this is related more to the problem of signal processing, right. What I am going to do over here is just talk a little bit about the implementation details alone. Okay. So in our case we are going to start off by considering one extreme version of it, right, where we set all the coefficients to 0.25. Now what does that mean? It means that if I take 0.25 and multiply it with these 4 values, that's effectively averaging the last 4 values, right. So if I gave it inputs like this, for example 4, 8, 12, 16 and so on, I also assume that initially I am 0 padding, meaning that if I don't have 4 inputs, the x of n-1, n-2, n-3 and so on will be assumed to be 0. So for the very first value I basically have the input 4 and the others are 0, 0, 0, and therefore the output comes out to be 1. For the next one it is 4 plus 8 and 2 zeros, right, which basically comes out to be 12 into 0.25, which comes out to be 3, and so on. So a quick recap of what we mean by fixed point format, right. In particular we use this notation Q15. What does that mean? It's basically a 16-bit number which is fractional representation, right. So basically we have one bit, the 15th bit indicates the sign, not exactly, it's actually more like it's a 2's complement number. If this bit is a 1, it indicates a negative number, if it's 0 it indicates a positive number, but as you know we are actually talking about 2's complement, so there is a slight sort of asymmetry in the range of numbers that is represented. In particular that range goes all the way from exactly minus 1.0 up to something that goes very close to 1.0 but not exactly, right. So what we have over here is if I treat a 16-bit number out here as an integer, right, a signed integer, a 2's complement value, then that number divided by 2 power 15 or 32,768 is the actual numerical equivalent value that I am trying to represent, right. So in other words, we have a range of values that can be represented using a 16-bit number, right, going all the way from this decimal value 32,767, which is not exactly 1.0 but very close, and that is represented using the hexadecimal value 0x7FFF. We can represent exactly 0.5, that would be 0x4000 hex, 2000 would be 0.25. So this is a useful number for us. It's basically what we expect to load when we are trying to just do a moving average, right. The value 0 itself would be represented like this, and this would represent the value minus 1.0, right. So why do we use this kind of an approach? Why do we use this kind of Q15 arithmetic? It's because for FIR filters typically coefficients tend to be, or rather we can always normalize them so that the coefficients are between -1 to +1, right. 16 bits is usually enough for a lot of cases. In reality, of course, it depends on the application. You might find that for certain kinds of video applications you might not even need 16 bits, you might need fewer than that. For audio you might need 16, you might even need a little bit more in some cases, right. And the interesting thing about the fixed point numbers is that they are very easy to implement in hardware, because the fixed point is just sort of something that we are interpreting the number to be. As far as the hardware is concerned, it is just a very simple integer, right. So everything is done using integer ALUs and shift operations, and 16 bits basically gives us a fairly high precision, right. 16 bits, every 3 bits roughly corresponds to 1 decimal digit. So this is about 5 decimal digits when we look at how accurately we are able to represent a number. So as I said, all of that is secondary. What matters to us is not even how this actually implements the FIR filtering, it's more a question of how does it integrate with the AXI bus, right. So what we are going to do over here is we are going to define a filter. I'll show you the code in a moment. We are going to have a filter which is not the simple straightforward implementation of the equation. It actually allows us to do something more than that. In particular, what it does is it defines a register map, right, and basically says, okay, this is a filter that's connected on the AXI bus. So what does the register map do? I have a register which is used to indicate the control, which is basically used for starting the filtering or for resetting it back to 0 and restarting and so on, right. I have another one which indicates the status. Are we done? Are we ready to sort of start filtering? What is the status of the system, in other words. There is yet another register which tells us how much data has been written into the system so far. We know there are only 4 coefficients, but the data could be much more than that, right. And in our case, we'll make a decision that I could have data of up to 32 values being written in, and I could do the filtering, or I could do it even with less, right. Coefficients, there are exactly 4 of them, right. And the reason why I am saying all of this is because this is going to be very similar to the approach that we used in the case of the FFT. Since I have 4 coefficients, I effectively have 4 different memory locations for it, but more importantly, I'll actually have arrays corresponding to the data. I'll have a range of addresses for the data input and a range of addresses from which I read out the corresponding data. And what this means is my driver, my device driver, will need to have some way by which it converts whatever input I am trying to get and puts it into the hardware module in the appropriate address locations, okay. So we are going to define, as I said, the full semantics of the register map. The control is going to be a read-write register. Bit 0 of this will be the enable signal, right, which basically sort of activates this. Bit 1 will be used to start. Bit 0, in other words, is just to sort of enable the entire filter, right, to sort of say that okay, it's active at all in the first place. But 1 is to actually start filtering new data, right. 2 is to reset the system. both of these are the W1P, meaning that they are pulsed signals. If I write and then I read back from there, I am not going to find a 1 corresponding to the bit that I wrote. It will basically send in a 1 and it will clear it immediately. Right? Now the status signal is read only except for one bit, which is a write one to clear, right? It has two bits that are relevant to us. One of them is the done bit and the other is ready, which basically says it's ready to accept new data. Okay. The length register is something that's going to be internally maintained. We'll see how we do that as part of the kernel device driver. But of course, we could also just write any value into it. As far as the hardware is concerned, you could just write a value into it. The coefficients are 16-bit Q15 values. The inputs, data in, is write only. You basically send data into the system using this, and the data out is read only. This is the output samples after filtering. Okay. All of this we will see as part of the Verilog code, roughly what gets implemented. What is also interesting is what the driver, the device driver code for this, the platform device driver, looks like. So the hardware architecture is going to be something like this. We will have a finite state machine which basically implements the actual filtering. It's going to be performing a loop which performs multiply accumulate operations by running over all the coefficients and multiplying the corresponding set of data that we have. Right? There are a set of registers which interact with this finite state machine. Those are basically going to be the control status, coefficients and so on. Right? You have the data input and the data output, right, which are basically connected to this, right. So the data input sends data into the processing and then it comes out and gets written into the data out. And both of these blocks ultimately are connected to the AXI light slave, as is this set of registers. So the AXI light interface basically is connected to the host, right, and from there all the data basically either I can write data into data in, read data back out from data out, or I can write into the registers or read data back out from the registers. All of these can be handled because of this AXI light interface that I provide over here. So the state machine, we'll look at the code to actually see how exactly it works. The computation itself, like I said, we'll be using a very simple sort of for loop over here. Actually speaking, what happens when you run a for loop is that it actually results in pretty much just unrolling all of these multiplications out and implementing them as, let's say, 4 different multiply operations in practice, right. So for loops are not directly implemented as state machines in Verilog. If you want something to be implemented as a state machine, you actually need to explicitly give it states, right. When you write a for loop, what happens in Verilog is it actually unrolls. It creates numtaps, number of copies of this particular part of the code, and adds everything together at the end. But in our case, we are writing Verilog, it is RTL, we hope it is synthesizable, but there is still one catch, which is that we are not yet simulating a post synthesis example, right. But it can be done. So Renault doesn't really care whether you are simulating a gate level netlist or some kind of behavioral Verilog. As long as you can verilate it, it will work.